Quantum mechanics, part 1 will cover mostly this book. Probably you all know this, and there is a new version of this book available, I think, with the addition of a second author, although this book is also quite sufficient. So the textbook is primarily J.J. Sakurai's Modern Quantum Mechanics. I will mention which subjects, which topics we will cover in a moment. But also I should mention that this is not obviously the only book available. There are almost hundreds of very good books available in print or in the soft form in the internet. You are free to study any of them which suits your taste. And there are several others, perhaps just for the courtesy to the authors, I should mention. For example, there is the Gottfried book. Gottfried, and I guess the new version includes a second author, Yen. There was an original version which is quite old, and that's also a very good book. These books are sort of complementary. Some of the issues which are more less discussed in one, it is covered in a slightly broader sense in the other, etc. And there are also, I should also mention the books by the Greiner. Greiner has several books. Some of them are more introductory, some of them are more detailed. Walter Greiner is the name, and sometimes he has other authors collaborating with him. I think Introduction to Quantum Mechanics, special chapters in quantum mechanics, Symmetry in quantum mechanics. So there are 3 of his books. He has about a dozen, really, in many different subjects and in the other fields of quantum field theory and relativistic quantum mechanics. But as far as our class is concerned, these 3 books, Introduction and the special chapters and the Symmetry, could be useful in certain discussions that we will be dealing with. The advantage of his books are that it's quite pedagogical. He goes through all the details. Sometimes you wonder whether, if you have those books, whether you need a teacher in the class. You can go and read it on your own, essentially. I'm joking, of course, that's not always the case, but useful books. And of course, there are classics like Merzbacher and Landau-Lifshitz. In the past, I have occasionally used that book for the 507. 508 is, of course, contains the relativistic issues, so it's not. And of course, these are classics. Landau-Lifshitz. I'm not writing the titles because it's so well known that when you enter the name of the authors, the books come out, so there's no need for the details. Okay. So these are the textbooks, and let me also go through the topics that I'm planning to cover. It could be plus or minus. Sometimes when the time permits, and if there are not too many holidays, official holidays, if we can save some time, we can add to it additional topics. Sometimes we may not be that lucky, and we may not have sufficient amount of time to go through all of them. But I will refer the topics I will list there I will refer to the section numbers in Sakurai's book. Therefore, you can, instead of writing all the details, I will just mention the chapters. Well, usually, as if everything goes as planned, The three chapters of this book is usually covered by all the teachers. So the first is the so-called fundamental concepts. I will elaborate the subtitles, but let me list the headers. The second is quantum dynamics. The third is theory of angular momentum. Well, that is a must. Either way, we will cover those. As I said, I will go through the subtitles. It's important. It will be sort of a warm-up towards the actual discussion. Well, there is a fourth chapter in here, the symmetry in quantum mechanics. For some reason or not, it is customarily skipped, But symmetry and the conservational laws are the most profound principles in the micro-universe, really. For example, the conservation of energy and conservation of momentum and conservation of angular momentum. Really, whenever you are involved with any kind of physics discussions, and it is understood that all these quantities are conserved. And there's a very good reason to it, and that is at the essence of almost all the modern discussions of physics. If there is a symmetry, there is a conservation law. And the actual proof of this beautiful theorem, very profound theorem, dates back to Noether, a German lady mathematician. So when you look at the symmetry, you deduce that there must be conservation laws, or if you are talking about conservation laws, obviously in the reverse direction, you can infer that there must be some kind of symmetry associated with this. I noticed that somebody calls the symmetry, I guess Fineman, change without changing. It is a beautiful, a very cryptic definition of symmetric transformation. Change without changing. Take off a sphere, rotate it around, and nothing changes, right, as far as mathematical property is concerned. Although you are inducing a change, right, you are rotating it, but the configuration and topology and the visual look and everything looks the same. It's a beautiful principle, but I guess for the concern of time, this is a 3 hours per week course, and in order to be able to proceed further, people tend to skip this. If time permits, I will try to jump into a few, at least, little sections of it, but otherwise I will follow the general trend and I will skip that section. So the next in line is, so 4 probably will be skipped, but 5 is the approximation methods. I will elaborate on this also, as this is the introductory day. I can afford to make an overall overview before actually reaching to it at the end of the semester. Approximation methods. You may say, why approximation? I will explain why we need to go through those approximation methods, obviously. And there are other issues like identical particles and scattering theory. Unfortunately, it is almost certain that there will be no time left to discuss those things. And it's a pity that we will not have time to discuss identical particles and scattering theory, particularly for those of you who didn't have the chance of taking 432, because it's usually in a very advanced level covered in that particular class, which I was doing it. So anyway, we cannot do much. So you'll go ahead, you'll proceed in your education without probably having a formal education on those issues. So what is expected is that you have to read, if your research is involved with those topics, then you're expected to go through on your own, learn it on your own. Because the proper place for doing that is 432. And unfortunately, it is not a must course. And it's a pity that it's not required for those who are at least planning to pursue their careers in physics. Well, anyway, in my future life, perhaps I may convince people that people should take 432 anyway. So let me elaborate on the subsections of those sort of global titles that I have mentioned. The fundamental concepts will involve essentially on the formal construction of mathematics. Some of them could be quoted as axioms or postulates of quantum theory, quantum mechanics, extracted from phenomenology, from observation, from nature, really. But I will elaborate on it. So it is, the fundamental concept is a mathematical and axiomatic formulations of the basic principles of the quantum mechanics as achieved around 1930, when the synthesis of the quantum mechanics was completed. Well, there are, for example, the Schweitzer experiment will play a crucial role in illustrating some of those basic principles. I will go through a little more details than the book really covers. And there is the cats and bras associated with the states in quantum theory, which I will also mention with a little more detail than the book. And the concept of operators, why do we need the operators? So notice that these are all mathematics. You may say cats and bras, which are elements of an infinite dimensional or finite dimensional linear vector space. You may say, oh, why all of a sudden we have to refer to those mathematical, rather exotic sounding concepts. You'll see the reason, the real physical, phenomenological reasons for that. And also bras and cats and matrix representations. And then comes the really crucial and central issue, measurements, observables, and the uncertainty relation. That is really, will be essentially the heart of the matter. So if you have to really explain someone from the external, from other civilizations, if you would like to send a message to them, what is the metaphor to describe your quantum mechanics, the level of knowledge as far as we understand the micro world? Well, you can use a cryptic expression of the uncertainty principle. Obviously, that represents a sort of one of the peaks of our understanding concerning. Well, there are further peaks, but at the elementary level, you can really you use that as a symbol of our understanding of the micro world. So we'll go through that in detail, both formally, and then we will talk about illustrated in certain examples. And there are also mathematical subjects like change of bases, so the concept of bases and change of bases. And then comes the position and momentum operators, which are very crucial operators for the reasons which I will go through in a little detail, further detail than the book. And then the translations. Well, translations in time and translation in space, which obviously this symmetry under those operations will lead to the conservation of energy and the momentum, which are well known at the classical realm, but it's going to be valid and true in the quantum regime. And then wave functions in position and momentum space. So out of those Hilbert space vectors corresponding to the states in quantum theory, we'll move to the sort of those older versions. Probably you know through your undergraduate education the wave function concept, which will turn out to be the coordinates in the position eigenvector bases or momentum eigenvector bases of these abstract vectors of the linear vector spaces. If this is finite dimensional, you are familiar with it. If it is infinite dimensional, they go by the name of Hilbert space. The difference, they are linear vector spaces which have infinite dimensions. There are infinitely many basis vectors which form a linearly independent sets. Anyway, you may say that's just a name. So that is the fundamental concepts, which should keep us busy for about 2-3 weeks. I will try to go through it as fast as possible, because I know that some of the roots of those sort of formal sounding discussions you have gone through at the undergraduate level, and either for 31 or 32. And in physics 300 type of courses, you have the background physics, more physics than mathematical formalism, but this will be sort of the overall formalism which will complete the picture, hopefully. In the case of quantum dynamics, we will talk about essentially the time evolution and the Schrödinger equation, the concept of space and the concept of state, which is a new concept in the quantum physics as compared to the classical. It is more elaborated in here. Also the operators, the commuting or non-commuting operators, eigenvectors of concepts is discussed in here. Now comes the quantum dynamics. Quantum dynamics, as the name implies, is the time evolution of the physical states. Whether they are taken from the Hilbert space as abstract vectors or whether you consider them as the coordinates in the position eigenvector basis, thus we call them wave function, and obviously they should evolve in time under the influence of an external agent or freely, because free particle problem is a very profound problem, as we will see eventually. So this quantum dynamics is the time evolution problem, essentially. Well, here we will discuss several alternative and equivalent pictures. You may say, why we need pictures? Well, of course, it will be elaborated further why we need different pictures. There are those famous pictures of Schrödinger, which is the default picture here. And there will be alternative pictures of Heisenberg and Dirac. Notice that all the great founding fathers of quantum theory, they have a picture on their own name. You know, it's nice, isn't it? It would be unfair that they didn't have those different pictures. And then, well, Heisenberg picture sort of puts the emphasis on the operators, and Schrödinger picture, as far as time evolution is concerned, Schrödinger pictures focuses on the states evolutions. And there is a nice discussion of this famous harmonic oscillator problem used in the context of Heisenberg picture that's going to be discussed in detail. And that's the simple harmonic oscillator. And then we will discuss the Schrödinger's wave equation in detail and what does it mean, how it is solved, and eventually what kind of physical predictions we can make out of it. And there is another beautiful chapter in here. I noticed that some people may have an inclination of skipping it in this kind of discussion, but I will not. Well, if nothing, it's for my personal taste. I have a special inclination toward this subject. It is the Feynman's post-integral formulation of quantum mechanics. Well, till now, all those discussions is you could be called the so-called canonical formulation. Well, canonical is historical, you know. It's based on the differential equations. All those time evolution equations are differential equations, at least in those versions. Now, this gentleman, Feynman, has developed an alternative formulation in the 1950s. Actually, it was contained in his PhD thesis. Although he has not received the Nobel Prize for that formulation, he has received it for another reason. It's the quantum electrodynamics, right? One of the most profound theories at the micro. The first profound theory at the micro universe. Eventually, it was followed up by others. It's the so-called standard model, and extending this electrodynamics to other interactions like strong and weak, etc. But QED, in short, quantum electrodynamics, is partly due to the efforts of people like Feynman, Schwinger, and Tomonaga, and they were awarded by the Nobel Prize for those achievements. That's beyond the level of this class. That requires quantum field theory, and so you have to go to a different class for that. And there's another beautiful discussion which I am very fond of myself personally, and that is the potentials and gauge transformations and gauge problems in the context of quantum theory. Well, nowadays, the modern physics theories, whether you are doing high energy physics, which is the leading cutting edge research, of course, particularly after that discovery of the Higgs and the completion of the standard model, and you don't have to be a high energy physicist. If you are doing modern physics, whether it's astrophysics or particle astrophysics or advanced high level condensed matter like graphene or all those things, Unit gauge theories. It is a beautiful thing, and it is, again, it's based on a symmetry principle, but this time the symmetry is not the space-time symmetries that I have referred to a few minutes ago. For example, if there are translation invariances along the time or along the space, you have energy and momentum conservations. And similarly, if you have a homogeneity in the space so that a system is invariant under rotations, you have conservation of angular momentum. And this symmetry is not a space-time symmetry. That is, those symmetries are internal spaces mimicking the external space symmetries, but so profound that, as I said, the standard model is built on it, and nowadays the new attempts of quantizing gravity is also referring to also using, or they're attempting to use those gauge symmetries and gauge transformations to achieve those. That completes the quantum dynamics. Notice that this is the formal mathematical development, that's the time evolution, that's dynamics, and there's time evolution, there's dynamics. And the third subject is theory of angular momentum. It's a very extensive subject. The subtitles are rotations and angular momentum commutation relations. That's really symmetry and conservation law connection, because they say rotations and angular momentum commutation relations. Obviously, you have to, first of all, using quantum mechanics, sort of mimicking those discussions associated with the momentum being the generator of the translations in space. We'll see that the angular momentum is the translation of the rotations, quantum generator of the rotations in the space. And therefore, it leads to a set of commutation relations, algebra and the group in a hideous manner. And then we'll get into the detailed discussion of spin one-half systems and finite rotations. Well, actually, the starting point of next hour of our fundamental concept will be based on that spin one-half systems. So spin one-half systems is a rather very profound subject in the context of quantum theory. And if you sort of generalize the concept of spin one-half systems to two-state systems in general, some of you who have experience in those things, you understand that the quantum information theory is based on it. So two states in quantum theory is more profound, more general than obviously what spin one-half problem implies. There are ammonia masers and all other things, the neutral K meson systems, neutral B meson systems, whatever. Or qubits and Boolean algebra is the mathematics associated with it. It's a very profound system. There is a new ball game under the title Quantum Information Theory. So I suggest that you really pay due attention to these spin one-half problems. It's very profound. You will be able to use it in many different areas of physics. And it moves into a little bit into the group theory, which is very good because group theory is a beautiful field of mathematics, and it has a kinship, a close relationship to those symmetric transformations relevant for the discussion of quantum theory. For example, you say rotations. And rotations is associated with, say, a 3x3 orthogonal matrices. Or you can look at the isomorphic versions of it, which is the SU2, 2x2 unitary, special unitary matrices. Again, they form representations of the rotations. When you look at it from that perspective, nature looks beautiful because that enables you to see the symmetries in a beautiful, more profound manner. So we will go through those discussions as the level and the time permits. And then we'll talk about the density operators and pure versus mixed ensembles. That's a very important subject, particularly in the context of quantum information theory. And I noticed that there is a warning in certain quick, short semesters, there is a tendency of skipping that section. I will try not to skip it. Therefore, I will try to include it. Although I know that Professor Sadi Turgut's lectures on quantum information theory has a very profound and deep discussion of that. If he's giving that course, I strongly recommend that you go and take it. And there are the eigenvalues, eigenstates of angular momentum. And also there's a special section on the orbital angular momentum, which is a very important problem. And probably that is the subject you all know most from your undergraduate education, the orbital angular momentum and the spherical symmetry and the spherical symmetric potential problems and solutions of Schrödinger equation for the spherical symmetric potentials like the hydrogen or the spherical oscillators, etc. That's very educative because you can solve those problems exactly and you can have a very good understanding of the essentials, the basic ingredients which go into that. That will pop up again in the context of approximation methods. And also there is the addition of angular momenta problem. You may say, why addition of angular momenta? Well, take the simplest of all the atoms. Everybody knows it nowadays. I guess it could be taught at the secondary educational level. Hydrogen atom is the simplest of all the quantum mechanical systems. There is a nucleus, which is the simplest, a proton and electron. And the potential tying these two together is the spherically symmetric Coulomb potential. So it's electromagnetism, really, which enters into this atomic discussion. So if you would like to have a proper discussion of hydrogen atom, apart from the naive discussion in the context of a Coulombic, sort of a Keplerian model, you have to include the essential structures of these entities carry. What do I mean? I will talk about it when I start the discussion. Electron and the proton. These objects carry mass and charge, quantized charge. And they carry spin, an intrinsic angular momentum. That's the angular momentum they retain when they are set at rest. Because when they are in motion, of course, there is an orbital angular momentum. That's also, you can carry it over from classical realm. And there is, this orbital angular momentum is an angular momentum due to the fact that they are moving. But when they are at rest, if they are not moving in space, if they still have an angular momentum, which could be tested, obviously, there are ways of probing those, then that angular momentum is called a spin. It's purely quantum mechanical, and there is no classical counterpart. So it's a tendency nowadays in the last quarter of the century to talk about the quantum mechanics in terms of those spin one-half systems or two-state systems. Forget about all the previous discussions because that's so quantum mechanical that you cannot have any trace of it at the classical region. That's patently quantum mechanical. So we will talk about, so then look at the hydrogen atom. If you would like to have a proper description of the hydrogen atom, then you have to go beyond the level of this Keplerian description. Take into account of the fact that electron carries a spin. If electron carries a spin, then when you are solving the Schrödinger equation by first identifying the set of compatible operators, so it won't be the ordinary orbital angular momentum alone. You have to go to the actually conserved total quantum angular momentum, which will be an addition of the orbital angular momentum of the electron plus the spin angular momentum of the electron. But these are operators, and they are non-commuting. They have non-commuting components. When you have such a complicated issue, which actually we will discuss the basics in detail in here, then you have to go through this new addition theorems of non-commuting vector operators having non-commuting components. It's a non-trivial issue, a beautiful issue. Essentially, all the architecture of the matter, atomic matter, is constructed on that addition of angular momentum theorems. I hope if you enjoy it yourself, I enjoy talking about it myself because the architecture of matter is a very profound and interesting issue. And there's here some nice exotic elaborations of this addition of angular momenta due to that other great scientist Schwinger. He uses oscillator model of angular momentum, which I will skip, I guess. That's a technical detail which should be left to the student to read on their own. And here there's another important theorem which I will try not to skip. Usually I notice that people tend to skip it because of time limitation. It is the so-called spin correlation measurement and Bell's inequality, Bell's theorems, and its generalizations. The quantum information theory is triggered by the paper of Einstein, as many of the other fields is triggered by Einstein. He was an opponent, funny enough, of the quantum theory during all his lifetime. Although he is one of the founding fathers, with that simple but very profound discussion of the photoelectric effect. Actually, it's funny that it's not the most formally deep work of his, but he's awarded Nobel Prize because of that work in 1905. He has carried out. Well, actually, Einstein in 1930s came up with a paper along with some of his collaborators and students. It's called the so-called EPR paper. He questioned the quantum theory of that day on the basis of completeness. He has raised some arguments to prove that quantum mechanics, as formulated using this Copenhagen interpretation, is incomplete. Amazing. Well, he had a long discussion with the other great scientists, Bohr, pro and con. One is trying to kill the quantum theory's Copenhagen interpretation. I don't want to call it killing the quantum theory. He was very unhappy about that Copenhagen interpretation, which I will mention under this title, Fundamental Concepts. But anyway, that led to this completeness discussion, pro and con, involving many very able scientists, eventually led to this important theorem by Bell, so-called Bell inequality. That was the end of that discussion, I guess. Unfortunately, Bell didn't live to receive a Nobel Prize for this. He died when he was quite young, according to these days' average lifespan. But when he was 62, he died. But the Bell inequality is contained in here. I will try to make sure that we go through that simple discussion. It's not a difficult thing, as is the case always. When something is simple and beautiful, it must be true and important. And this theorem is very easy to understand because it can be simply formulated. So I'll try not to skip it. And it's the last section of it goes under the theory of angular momentum here, with Bell inequality. So I skip the symmetries. Hopefully not, but it's very likely that I will skip it. Because the first section in here, 4.1, symmetries, conservation laws, and degeneracies. At least I would like to talk about that first section, if not others, because there are discrete symmetries like parity, space inversion, lattice translations, blah, blah, time reversal, which is a very profound discussion, which may be a little beyond the level of this class. That's one of the reasons why people tend to skip it. But the first section sort of sets the stage for understanding if there is a symmetry, there are conservation laws and vice versa. Not only in space-time, but also in internal spaces, which is the gauge theories is based on. Then comes the approximation methods. If I don't finish it in a few minutes, I will continue this discussion because I'm trying to tell you some sort of overview type of stories while I'm going through the sections to motivate yourselves why we will go through all those. Although when time comes, I will go through them in detail again. Approximation methods. The need arises because when you write down an equation of motion, quote unquote, sort of, say they may be analogous to the classical equations of motions of Newton's or Lagrange's or Hamilton's. You know, if you're at the classical region, you have a set of equations of motions, right, to describe physics. And they work successfully. Although they failed at the micro-universe, at the atomic level, they work at the macro scale still after 300 or 350 years that they have been discovered successfully. If they don't work successfully, we wouldn't be able to send a satellite and put it in an orbit in the moon or in the Mars or etc. So these laws are beautiful laws. They work perfectly at the large scale. At the micro scale, they fail, but this is the reason why we go through this. We are trying to construct alternatives which would function and which would enable us to understand the nature of the microworld and the function, the operations that are taking place at the microworld. And some of the equations which will emerge in here, which goes by the name of Schrödinger or Heisenberg or Dirac, alternatively in 3 different pictures, they are really equations of motions which describe the time evolution problem. That's the quantum dynamics. So you may say, in short, in the undergraduate level probably that's how they start. Here is the Schrödinger equation, here is the wave function, and the wave function mod squared describes the probability density. So let's solve the Schrödinger equation and let's work out the expectation values, the most important expectation value being the energy, right? You solve for the energy spectrum. Fine, in principle okay, but provided that you can solve those exactly and analytically. Most often than not, life is not that simple, and the interactions are not as simple as the Coulomb one or the R² one, which describes the spherical oscillator. And the actual dynamics involve more complicated forces and interactions, and then actually solving that equation may not be possible exactly. So you have to resort to approximation techniques, that's why. And there are several approximation techniques available. The first, the most popular one, goes by the name of Rayleigh and Schrödinger. Well, for the credit of Rayleigh, because apparently before the turn of the 20th century, this gentleman, while he was working on the sound waves and fluid dynamics, he has developed those approximation methods for the particular differential equation he was dealing with. Don't forget that in principle, we all reduce all these beautiful equations of motions to differential equations of second degree, mostly in time, or second degree in space. So whatever the underlying physics is, there is an underlying unity in mathematics. You solve differential equations specifying the initial conditions, etc. So the gentleman, Rayleigh, had developed a formalism. Schrödinger adapted it to his version of the equation, Schrödinger equation, which is again a second degree differential equation for the stationary states. So I will not talk about this. I will try to talk about this here. It's a difficult problem. Well, it is physically, conceptually simple, well-defined. There is a beautiful algorithm behind it. There are degenerate problems, non-degenerate problems. We'll try to discuss them all in here. And probably that will be the end of the semester with the Rayleigh-Schrödinger. Time-independent case, time-dependent case, probably time-dependent case, I will postpone it to 508. Because there will not be time enough for that. Actually, that is the most interesting part of the problem, time-dependent one, because most of the interactions are electromagnetic interactions. You send light on the atomic system. Light is an electromagnetic wave which oscillates, so there's time dependence is clearly built into that. But we will not have time for that. By the way, that's not the only approximation method available. There are different books and different research fields which uses different versions. One is very popular, one is a variational method. And there is a beautiful generalization of it by Fineman and Hellman. So variational methods is a very involved field, and most of the atomic and molecular physics research uses that. I'm not going to get into that, variational techniques. And there are also another beautiful method, which is called the Wkb Approximation Method. Again, we have no time to discuss all those. So out of all the possible and beautiful set of approximation techniques, which is based on the need that we cannot solve the Schrödinger equation exactly. In those cases, we have to resort to one of them, and the most popular one is the Rayleigh-Schrödinger, which I will discuss, and probably that will be the end of our semester for this year. So this was an overview with some details in it. Next hour, I will, after the break, I will go through some of the essentials from classical to quantum, and then I will start the fundamental concept based on the Stengerla experiment. I think that's a good point to stop for today, for this moment.